We've got some new products, a new architecture, new initiatives to announce today. Here's the obligatory statement. I'm very intentionally going to make forward-looking statements. And those forward-looking statements have risk and uncertainty associated with them. But let's face it, if there wasn't risk and uncertainty, it wouldn't be worthwhile, right? Okay. Speaking to this audience, you guys are very familiar with the concept of data growth and the explosion and just the exponential advancement of data, the volume, the variety, the velocity of data. Data has changed significantly over time. As Jay mentioned, I've been in the business 30 years. I can remember when data primarily was row-column spreadsheets running in traditional storage infrastructure in traditional data center architectures, and nothing could be further from that today, certainly as we see everything evolve around it. Data evolved to a form of communication, and certainly today we see the rich forms of communication related to data in its various forms. Data evolved to a means of efficiency. And it touches all of our lives, our private lives, our professional lives. Really, there's no dimension of how we live and operate that isn't affected in some way by the efficiency, the automation, whether it's how you expect service from your healthcare provider to, you name every dimension of your life. Data is efficient, and it drives efficiency in how we live and operate. And then it's clearly evolved from there as well, data even as currency. We see companies actually buying and selling data, and data itself becomes a form of currency. So data has evolved significantly over time in richness and in value. At Western Digital, we think about data in two very large categories, big data and fast data. I think everyone understands these concepts, right? Big data is the process of coalescing large amounts of unstructured information together and then driving reasoning across it, cognitive workflows, analytics, AI, machine learning, not just buzzwords to get a bunch of social media hits, but actual workloads that are driving the majority of where we see data growing today significantly. Big data allows for deeper levels of insight, understanding really what's going on in a business with a customer base, where the market is moving, the competitive landscape, certainly being able to predict the future, whether it's weather forecasting or the market or competitive moves in the industry. The final one is precision. Big data certainly allows a degree of precision that is unprecedented today. You could just look at personalized healthcare as an example, where big data is being used to analyze into the individual genomic sequence of cancer cells, allowing for unprecedented levels of personalized medicine. This is a field that's all enabled by big data. It's about scale. Related to that, and more closely than you might think, is this concept of fast data, bringing data and compute closer together, whether it's collecting data as it occurs, capturing it as it's created in real time, whether it's through multiple endpoints. There was a presentation this morning on IoT and the explosion of sensor data that we'll see just in the next few years. But it's about driving real-time decisions, real-time results, moving at the speed that data is being created, making decisions on it, in line, on the fly. All of this, again, interrelated, primarily through analytics. Analytics is by far the number one workload in the cloud. And we certainly see that in private enterprise and scale-out data centers as well. We've also seen a significant change recently, just in the last few years, about the relationship between applications and data. If you look at the primary life cycle of data, or the primary steps that you would go through in data creation, it's the creation, it's the store, it's the access, it's the transformation. Heretofore, largely, that has happened primarily between a single application and a data set running on maybe an application running on a number of servers, but primarily the application creates the data, it stores the data, it accesses the data, it transforms the data. What we see emerging rapidly and in many ways and in many markets is this notion of this complex mesh now of applications and storage and consumers and producers of that data that creates this complicated web where nothing is static. There's no more static. There isn't, well, my application needs to add some new users so I can scale up a little bit of memory, I can add a little bit more storage, but I'm just pretty much linearly scaling the environment. In the example on the right, that's very difficult to do. It's hard to anticipate the pressure that this mesh of applications and users and data storage and access and transformation is going to put on data center infrastructure. We believe that not only an evolution, but a revolution is required in data infrastructure to service this kind of an environment. And there's evidence to say that this problem is getting worse. There was a study recently that surveyed mid-sized and large enterprise IT users. Approximately only 45% of the resources, the compute and storage resources, were actually being utilized in the data centers on average. And that's not atypical. This isn't a cherry-picked data point. That's actually quite common. And the reason is, if you're building IT infrastructure that fundamentally has to be flexible, but it's built out of inflexible building blocks, you're going to wind up with a lot of over-provisioning. You have to. It's the way that data center practitioners have to respond to the dynamism associated with today's workflows and environments. These users also said at least 70% of the time they found significant inefficiencies in how they're provisioning, how they're orchestrating compute and storage resources for these applications. And it's getting more complex. These numbers are not trending more positive, they're trending less positively. So this really brings us to a conclusion here to begin with regarding the demands on today and tomorrow data infrastructure. Scalability is important. The ability to scale compute and storage independently is fundamental. Workloads sometimes demand more compute, they demand more storage. The storage has to scale against its SLA, whether it's a capacity or a performance-oriented storage tier, it has to scale. Efficiency is critical. I talked about the utilization rate in a data center. IT budgets being what they are, the progression of technology, the insatiable demand for more and more storage and compute, all of these put incredible pressure on efficiently utilizing the assets that you have. Whether you're paying for them as you use them or you're buying them through traditional CapEx means, it's critical that we raise the level of efficiency in the industry. We cannot be successful if the average enterprise IT data center is running at 45% utilization. Agility, this concept of being able to respond to changes in workflows and environments. And there certainly are a set of use cases in data centers where the applications are more monolithic, they're very predictable, it's a predictable use case, you've got your compute, you've got your storage, you're good, and it doesn't change that often, and that's great. We're not looking at addressing those problems because frankly a problem doesn't exist there, but that is not predominantly what we see in the market today. We see incredible pressure on infrastructure agility. If you were running a data center and you had not 5 or 10 racks, but 100 or 500 racks of infrastructure, your concern is, how can I, in an agile way, get the most out of every floor tile in that data center? And how on earth can I orchestrate that environment for the changes that are coming in my business every day? And then finally, performance. Clearly, this room is filled with people who have spent a lot of time and effort innovating in the area of semiconductor-based persistent storage. Increasingly, the challenge is, how do you deliver that performance of that media to the application layer? So we need a solution to these challenges. So along the way, the industry has evolved. We've seen several evolutionary steps in data center infrastructure, data infrastructure, and they've all kind of picked a little bit at some of these problem points. The first one that we saw a number of years ago emerge was this notion of converged infrastructure. Converged infrastructure was primarily the integration of proprietary compute and networking and storage solutions into a rack-level solution that simplified the purchasing experience, it simplified the deployment experience, it may have simplified the support experience around that. But the step ahead that converged infrastructure really drove was, maybe for the first time, at least in a holistic way, we started thinking about the problem of compute and networking and storage as a whole, as a single unit, as a single SKU, for instance, that it was sized to a particular application, still very rigidly configured, and it was proprietary infrastructure, but at least it thought about compute and networking and storage a little more holistically. From there, the industry evolved to hyper-converged infrastructure, and everyone knows what this is. It's predominantly software-defined storage stacks running on more general purpose, call it commodity or not, but more general purpose server storage infrastructure, DAS architectures. This was a step ahead because it became all the more simple to build up a rack of infrastructure and deploy a software stack on top of it. The challenge, of course, is even in a hyperconverged environment, decisions have to be made regarding what kind of SKUs are you going to buy. The catalogs, the product catalogs of the hyperconverged manufacturers are pretty deep. There's a lot of SKUs in there, and you have to pick and choose. You have to decide, how am I going to configure this infrastructure? And you have to anticipate that I hope the workloads don't change too dramatically. We think the industry is moving towards composable infrastructure. It's not necessarily a brand new concept. You've heard it before, I'm sure. And a lot of the initiatives heretofore in the industry have been around the modularity of server designs. The ability to mix and match modules. You can mix a little more compute in, a little more storage in, more flash, more hard drive. And you can orchestrate them together, and it simplifies the purchasing experience. It gives you some finer granularity in your ability to pick what kind of a platform you're running on. And it's a nice step ahead. It certainly begins to disaggregate a bit compute and storage, but there's still that notion of a physical environment around it that kind of defines the sandbox, the building blocks of the unit of resource that you're working with. We think a revolution is required. We think the industry is poised based on open standards, such as NVMe and NVMF, to take the next step. Take the next step into something we call software composable infrastructure, or SCI. This graphic kind of helps compare and contrast the two a little bit. On the left is a typical HCI stack. You're choosing a particular server SKU, server storage SKU, and you're composing them together. But let's say in a flash-intensive workload, you're going to have some underutilized resources, perhaps. Maybe compute, maybe HDD in there. On the right side is a graphical representation of what software composable infrastructure affords, what it imagines in terms of independent resource tiers of compute and networking and storage. And forget the boxes. It essentially erases the physicality of what a rack mount box is. And it exposes those resources, the compute resources, the network resource, the storage resources to a fabric environment that can be, through software means, composed together. It addresses those pain points, the scalability, the efficiency, the agility, the performance, we think in a very robust way. It also applies to a capacity-intensive workload as well. There's much of the composable infrastructure dialogue in the industry has been around flash technologies, and that's great. SSDs play a huge role in today's data center. But we also think it ought to apply to capacity workloads as well. The net takeaway here is that we think through composable infrastructure, software composable infrastructure, greater economic advantages are realizable, certainly the agility, the efficiency, because you're provisioning exactly what you need for the workload you have today. And you can change it over time. Because it's software composable, there's not a physical mechanism associated with reprovisioning or replumbing compute and storage and network, or compute, network, and storage together. And it's applicable to all environments. Hyperconverged infrastructure is great. It runs in a hypervisor environment. Not all applications are intended to work in those environments. The great thing about software composable infrastructure is it doesn't preclude anything. It can be virtual, it can be container-based, it can be bare metal, and all the applications on top of that. Our own studies show that I think significant savings are possible with a software composable infrastructure approach. 50% initial savings in CapEx in the upfront purchase, and 40% in the cost of ownership over time. So our vision for composable infrastructure is built on these 4 pillars, and each one is critically important. The first one is open. We think that in order for the industry to accelerate in this direction, this standards effort should be a very open approach. We're building an ecosystem of partners to help us define and refine these ideas. And when I say open, I mean not just the software API, you might imagine that, but also the hardware form factor as well. I'm going to introduce to you the concept of some new products that we're demonstrating, and our intentions are to open up the hardware form factor for those devices. We believe that anyone should be able to build this infrastructure, and anybody should be able to orchestrate it through an open API to manage this environment. The second one is scalable. It's fundamental that we be able to scale compute and storage independently. So there should be no boundaries on the scalability of this solution, whether it's a very high-performance flash-based media or deep capacity-oriented HDD for big data workflows or long-term digital asset preservation. It's also very important that the solution be disaggregated. When I say disaggregated, I mean physically disaggregated. We need to get rid of the concept of server storage SKUs. We need to get to a model where the resource tiers of this solution are truly physically separated from each other. That's how you can actually drive software composability into the ecosystem. And of course, extensible. And by extensible, I mean it's not just SSD. It should apply equally to rotating disk as well. And these media tiers, think about them almost as storage as a service peers on a fabric that have a certain SLA, a certain durability, a certain IOPS and latency profile associated with them. But it ought to work the same way. You should be able to orchestrate or compose in the same exact way, whether you've got a deep tier or a high performance tier. And this shouldn't necessarily just stop at the data fabric. We believe that software composable infrastructure in time, over time, needs to evolve to memory fabrics as well. The idea of no physical systems at all, only composed systems, only systems that are logically composed from memory to compute, to networking, to storage resources seamlessly. No established hierarchy. These are systems of peers. The peers communicate with each other, and they come together to compose a logical server storage solution for a given application workload. To enable this vision, we have to create something new. This doesn't exist today. We're announcing it today. This idea of a fabric device. We intentionally chose this word, this combination of words. Typically when a company, certainly Western Digital, we talk about devices, we're talking about hard disk drives or SSDs. We're talking about something that has either NAND or rotating disk behind a controller, and that controller speaks to an I/O bus. That's typically what we mean when we say a device. But we've definitely introduced here a new concept around a fabric device. Again, media behind a controller that speaks to a fabric. It's very important, whether it's flash or disk or compute. These fabric devices are essential to building the framework of a software composable infrastructure approach. Very simple building blocks. It's critical that the fabric endpoints be simple devices and peers of each other. This accelerates our ability to get technology to market. If you think about the idea of a fabric-attached storage device with a certain SLA and a certain performance profile attached to it, delivering devices at that level of aggregation allows us to very quickly innovate in the media behind it. What today might be a hard disk drive-based fabric device that may have 50 terabytes of capacity, tomorrow it could be based on QLC. Different SLA, but similarly used in terms of its use case. So we can accelerate technology to market with this approach. It's important there's multiple paths to the device. We want to build highly available architectures. And the fabric devices, the NVMe fabric devices, are sized according to the performance of the media and matched to the performance of the fabric. These are important characteristics. You can see with fabric devices that the construction of purpose-built data center infrastructure becomes a very straightforward task. The process of sizing compute and disk and flash into a rack, composing it on the fly, being able to recompose it and repurpose it through software mechanisms gets to be very exciting. And if you're that data center operator with 50 or 100 or 500 racks, this becomes incredibly valuable to you. You know that you can, through very simple mechanisms, recompose and repurpose the data infrastructure in your environment to the workload dynamics that you have today. So today we're introducing something we call OpenFlex. OpenFlex is Western Digital's identity for our fabric-attached devices and the architecture to go with them going forward. Shown on the page here are examples of products that we're demonstrating today on the show floor. The first one I'll talk about is the F3000. The OpenFlex F3000 is a fabric device. It's built for very high performance, low latency workloads. As I mentioned, it's media behind a controller attached to a fabric. It varies significantly in capacity, from a few terabytes to many, many terabytes. The enclosure that houses up to 10 of these F3000s is something we're calling the E3000. Do not make the mistake to think about this as a JBOD or a JBOF architecture. That enclosure is simply there to hold the fabric devices, provide power and cooling, yes, but those individual fabric devices, one of which is slightly pulled out there, is an autonomous fabric entity. It's a peer on the fabric. It acts as a fabric-attached, high-performance storage device. It's a fabric device. Similarly, on the right side is our D3000, a 1U enclosure with very high-capacity storage in it. It in itself is a fabric device. These fabric devices are the consumable, kind of customer replaceable unit. This is the crew and crew in the field. The industry is moving towards software-defined stacks that can deal with vast amounts of data across various failure mechanisms in the fabric environment. These things are built to orchestrate those environments. The F3000 and the D3000 are being demonstrated today running a multi-vendor, multi-application, multi-software stack environment in our booth. I'll talk about it in a second. And again, don't think about the E3000 as a JBOD. It does not aggregate the performance or the connectivity of the fabric devices that are within it. As important as the hardware is, and it's very important, the concept of fabric devices to enable this vision, the software side is even more critical. And we're looking to extend the very good work going on in the industry. Clearly, there's a lot of work going into Redfish and Swordfish with physical server management, Swordfish, the logical storage management side. We're introducing an API we call Kingfish. Clearly, we want to build on the work that's going on, but it's necessary to move from just being able to physically enumerate the endpoints of a fabric and just being able to logically provision them as a subservient or a target device at the end of an I/O bus. We need to add some new functionality to this environment through this API that allows us to orchestrate at the fabric level fabric devices as peers of the compute and the networking resources. So Kingfish is our environment to do that. We're working on this. It's an open API. It's certainly, as I mentioned, built on existing open standards. Our intentions are to make this absolutely open in the industry and to work with the industry to bring this to fruition. It's unified across all of the data infrastructure, flash, rotating disk, for delivering simplicity at scale. This is designed to be an incredibly simple environment to orchestrate and administrate. We're providing APIs to the public to accelerate innovation and market adoption. It's a critical part of our strategy and our vision for enabling this in the industry. We're also building on top of that our own orchestration layer. We expect that a number of companies will want to adapt their orchestration layers to this API, but we're certainly bringing one to market as well, focused on rapid composability, the ability to generate new instances in seconds, and optimize the infrastructure to the needs of a given application or workload. So we'll have our own product built on Kingfish, but we expect an ecosystem of partners to be innovating and advancing their own work on top of it. I mentioned the broad ecosystem. We're building an ecosystem around software composable infrastructure and the Kingfish API. You can see some of the names here, a combination of large companies, some startups, some component providers, infrastructure providers. We're going to expand this. We're going to continue to expand this. It's important that it's a big group and working with the existing bodies in the industry to bring this to reality. Incredibly important, this ecosystem and its growth. So Western Digital OpenFlex. It's, First and foremost, if you remember something about it, it's open in the name. We're committed to an open approach to software composable infrastructure we call OpenFlex. Building an ecosystem around this is critical, as I said, to accelerate market adoption. And we think it's important for us to lean into this with real products that we're demonstrating today to accelerate the adoption of this. The world trusts their data to Western digital products. Our intentions are to invest significantly, as we have been, and will continue to invest significantly in bringing an ecosystem, a hardware and a software ecosystem that's open to the industry around this technology. Okay, thank you very much. I appreciate your time.